Hello, I tell you video 7. This is the worst drought in recorded year. Births. History. This is the worst drought in recorded year. Births. History witnessed the United States facing the worst drought in recorded history, a continental crisis unfolding even before the predicted climate triggers arrive. This pre-trigger drought is reshaping agriculture, water systems, energy grids, and ecosystems, revealing a story of unprecedented systemic stress that affects not just America, but the global food and water network. Discover the hidden feedback loops and extreme conditions that make 26 a year unlike any other. In this video, we dive deep into the science data and environmental mechanisms behind the 2026 drought, exploring record-low snowpack, heat amplification, soil moisture feedbacks, wildfire acceleration, and impacts on crops and livestock. We examine the interconnectedness of water, energy, and agriculture across multiple U.S. regions, and highlight the global ripple effects on markets and food security. By the end, you'll understand how pre-trigger conditions shape outcomes long before climate-forcing events like El Niño fully manifest, providing insight into both environmental science and systemic risk. If you find this exploration insightful, please like, subscribe, and share to help more viewers understand the hidden mechanics of droughts and global climate systems. Your engagement helps the channel reach audiences seeking awareness, education, and actionable knowledge about Earth's environmental feedbacks. For more journeys into extreme weather, climate science, and environmental systems before sleep, check out our playlist, Discover the Universe Before Sleep, Climate Earth Stories. Explore related videos on mega droughts, heat amplification, and systemic environmental crises. Hello there and welcome to Discover the Universe Before Sleep, where we blend storytelling, science, and relaxation to explore Earth, space, and environmental phenomena before you drift into slumber. Our content uses AI tools as illustration, suggestion, and educational support, ensuring clarity and accessibility while helping viewers understand complex topics. AI is not the source of factual claims but a tool to guide explanation. USA Drought Mega Drought 2026 Pre-Trigger Climate Video Tags. This is the worst drought in year. History 2026 year. Drought crisis explained. Mega drought impacts on agriculture and water. Extreme U. Drought 2026 Science. Discover the universe before sleep. Pre-trigger climate events and droughts. Sleepy science, drought and environment. Record-breaking amount. BES. Drought explained. Global food and water network risk. Heat amplification and soil moisture feedbacks. Chapter 1. The pre-trigger of a continental crisis. Imagine waking up to a world where half the country is already parched, the rivers whispering a story of disappearance, and the soil beneath your feet silently telling you that something has gone catastrophically wrong. This is not a scenario in some dystopian future. It is the United States in early 2026, experiencing the worst drought ever recorded in modern history, even before the climate event predicted to make it worse has fully arrived. If you live in America, this is your story. If you care about food, water, or the air you breathe, this is your problem. And you need to know exactly what's happening before the dominoes of nature fall further. In the first 3 months of 2026, January through March, the U.S. shattered a 131-year record for dryness. These weren't incremental deviations. The Palmer Drought Severity Index, DISI, which integrates precipitation, temperature, and soil moisture, recorded a national value of 7.85 in March, second only to the Dust Bowl of the 1930s. The United States Drought Monitor reported that over 60% of the contiguous states were in drought, with nearly 44% in severe to exceptional categories. That means this isn't just a patchy, regional weather hiccup. This is a continental-scale crisis already writing itself into history. But why should you care? Because drought isn't a distant statistic. It is the invisible force reshaping the landscapes we live on, the food we eat, and the stability of our environment. Wheat fields in Kansas are failing before the planting season even fully began. Reservoirs along the Colorado River are approaching levels so low that hydroelectric turbines are on the brink of shutting down. The Ogallala Aquifer, a lifeline for irrigation across the southern plains, is being drawn down faster than it can replenish. And here's the cruel twist. The climate driver that forecasters warned would intensify this crisis, a potential super El Niño, has not yet even fully arrived. So why keep watching? Because what you're seeing right now is the pre-trigger. Understanding it gives you a lens to anticipate what's coming next, and to feel the urgency that numbers alone cannot convey. This video will take you step by step across the United States, from the parched plains of the Midwest to Florida's unprecedented drought, and across the western mountains where snowpack, a natural water reservoir, is vanishing. We will explore why the drought is accelerating, why heat and soil feedbacks are amplifying it, and what it means for agriculture, water, and energy systems. By the end, you'll see this is not just a story about dry fields, it's a story about systemic vulnerability, cascading impacts, and the invisible crises shaping our future. If you're ready to see the full picture, stay with me and take a moment to like the video. It helps this story reach those who need to see it, those who are grappling with similar uncertainties, and those who seek to understand our world before it slips quietly into crisis. Over the next chapters, we'll uncover the mechanics of this drought, the atmospheric patterns holding it in place, the role of heat as a multiplier, and the hidden feedback loops that make this event unlike anything the U.S. has seen before. Curiosity alone won't prepare you, the knowledge will. And as we explore, let your mind drift with the data, the stories, and the science, like a journey through the universe itself, right before sleep. Chapter 2, Florida's impossible map. Even before the main climate trigger has fired, something almost unthinkable is unfolding in Florida. 99% of the state is in drought, a place where humidity and afternoon thunderstorms usually define life, where cypress swamps and river systems are engineered by nature to thrive on water, now lying parched under a relentless high-pressure dome. The culprit is the westward expansion of the Bermuda High, a semi-permanent high-pressure system over the Atlantic that has shifted inland, trapping warm, sinking air above the southeast and suppressing the very clouds that would normally deliver rain. This isn't a subtle anomaly, it's a continental signal manifesting locally, a pre-trigger phenomenon that turns a state accustomed to water into one at the edge of ecological collapse. Pine flatwoods, palmetto scrub, and dense subtropical forests, normally saturated and resistant to fire, are now fuel waiting to ignite, while soils dry at unprecedented rates, losing the natural air conditioning effect that moist ground provides. The surrounding southeast states, Georgia, South Carolina, Alabama, Mississippi, mirror the same pattern, creating a nearly continuous swath of extreme drought across a region that climatology never predicted would suffer this way this early. And yet, these atmospheric conditions are only part of the story. Heat amplification plays a decisive role. Air temperatures in April 2026 remained far above historical averages despite the typical cooling influence of on the neutral Pacific, making the atmosphere thirst IER, accelerating evaporation from soil, vegetation, and surface water, and deepening drought stress. Meanwhile, the soil itself becomes an active participant. Depleted moisture suppresses local cloud formation, allowing more solar radiation to heat the surface, which dries it even faster, a self-reinforcing feedback loop that no rainfall can reverse instantly. Farmers across central Florida and the Panhandle are already confronting the prelude to crop failure, checking irrigation projections against reservoirs that are falling faster than any seasonal norm, while wildfire planners adjust for a fire season months ahead of schedule. What makes this map so impossible is not just its scale but its timing. All of this is happening before the super El Niño emerges, meaning the atmospheric system itself has already created conditions more extreme than forecasters expected. The question that lingers is unsettling. If Florida and the southeast are this stressed now, What will happen when tropical Pacific warming finally interacts with this locked atmospheric pattern? By examining Florida's impossible map, we see how a single atmospheric configuration can simultaneously stress a typically wet region, create a pre-trigger disaster, and set the stage for cascading ecological, agricultural, and economic consequences, showing that drought is not merely a regional inconvenience, but a planetary-scale phenomenon with local surprises waiting to unfold. Chapter 3: The West without snow. While the Southeast struggles under unprecedented dryness, the American West is silently facing a crisis of a different kind. Snowpack, the natural water reservoir that sustains rivers, farms, and cities, is disappearing at record rates. On April 1st, 2026, 8 western states simultaneously recorded all-time record low snowpack levels: Arizona, Colorado, Idaho, Nevada, New Mexico, Utah, and Wyoming. This is not a regional anomaly or a short-term weather blip, it is a continental signal of water scarcity. Snow water equivalent, SWE, the metric that quantifies how much water is stored in the snow, showed values at 12% of the historical median in Oregon, with other states ranging from 20–30% of normal. Even more alarming, 75% of snow-tel monitoring sites reported snow completely melted more than a month ahead of schedule, stripping the natural delay mechanism that spreads water availability across the dry season. Without this slow release, rivers run low early, reservoirs fail to capture runoff, and irrigation systems that rely on gradual meltwater face collapse. In the Colorado River Basin, temperatures were anomalously high, up to 13.7 above average, meaning much of what would have fallen as snow instead ran off immediately as rain, accelerating the deficit. This is a pre-trigger scenario. The system is already structurally compromised before the anticipated Super El Niño forces intensification. Hydropower faces a direct threat. Lake Powell sits at 23% capacity, dangerously close to the minimum power pool needed for turbines to operate efficiently. With snowpack gone, inflows will not recover, and reservoir-dependent agriculture, cities, and electricity grids are on borrowed time. Farmers face the stark reality that no summer rain can replace months of absence. No. Every inch of missing snow represents millions of gallons of water lost to a parched landscape. The western mountains, once invisible buffers, now act as silent witnesses to a water crisis unfolding before the primary climate driver even arrives. The pre-trigger narrative here is as clear as it is unsettling. The West's water budget for the entire year is effectively written by February and March snow measurements, leaving millions dependent on a system already pushed to its structural limits. And while the Southeast bakes under sinking air, the West watches its frozen reservoirs vanish, reminding us that drought operates not only through the absence of rain, but also through the failure of natural infrastructure, the snowpack itself. Understanding this prelude is crucial. It reveals the baseline state of stress across multiple systems, showing that the worst impacts may already be locked in, even before the external forcing has had its say. Chapter 4: The Pattern Lock. The extraordinary drought gripping the United States cannot be explained by precipitation deficits alone. From Florida to the Rockies, a single atmospheric configuration is enforcing dryness across multiple climate zones simultaneously. Scientists call this a pattern lock, a stationary ridge in the upper atmosphere that stalls weather systems, deflects moisture, and suppresses precipitation. These high-pressure peaks, part of the larger Rossby wave structure, normally move eastward, allowing wet and dry periods to alternate across the continent. But in late 2025 and early 2026, the waves slowed to near standstill, creating a blocking high over the U.S., compressing the flow of moist air from the Gulf and the Pacific. The Bermuda High's westward expansion over the southeast is the eastern expression of this ridge, while the western U.S. experiences prolonged dredging and heat amplification. The result is continental coherence. Drought conditions simultaneously peak in areas that historically experience very different climatology. The significance of this pre-trigger is profound. Droughts usually evolve regionally, giving humans time to adapt and respond. Here, the log suppresses rainfall across the board, accelerating evaporation, reducing soil moisture, and forcing early vegetation stress, all while precluding any relief mechanisms. This persistent atmospheric configuration is likely influenced by a weakening jet stream, itself a consequence of amplified Arctic warming, which reduces the equator to pole temperature gradient and allows slow-moving wave patterns to stabilize. What we observe in 2026 is an interplay of physics and climate forcing. The slower the waves, the longer the high-pressure ridges persist, the deeper the drought. The pattern lock creates a predetermined template for drought impact even before El Niño arrives, shaping soils, rivers, reservoirs, and ecosystems in ways that will magnify the eventual climate forcing. In practical terms, this means farmers, reservoir managers, and wildfire planners are operating within a system whose baseline has already shifted. The atmospheric scaffolding that normally moderates variability has disappeared, and the drought is self-reinforcing. The pre-trigger is no longer theoretical, it is observable. As the pattern lock maintains its grip, the United States enters a state of systemic drought, one in which every action, from irrigation choices to wildfire preparedness, is made under conditions already far outside historical norms. The scientific lesson is clear: drought is not simply a function of rainfall. It is a complex interaction of heat, moisture, and atmospheric structure, and in 2026, that interaction is fully aligned to maximize stress across the continent before any major tropical forcing arrives. Chapter 5: The heat multiplier. Drought and heat are intimately linked, yet 2026 has revealed the magnitude of their interaction in ways that surpass historical precedent. Across the United States, temperatures in the first quarter were significantly above historical averages, even during what should have been a moderating lull in a neutral phase. This anomaly is critical because warmer air has a higher capacity to hold water vapor, approximately 7% more for each degree Celsius increase, a principle described by the Clausius-C-LA-Perrin relation. What this means in practice is that the same rainfall deficit that would have produced moderate drought in cooler years now drives severe to exceptional soil moisture depletion, accelerating crop stress, reservoir drawdowns, and vegetation die-off. The atmosphere, thirstier than historical norms, pulls moisture from soils and plants at an unprecedented rate, amplifying the drought even without additional reductions in precipitation. In the western United States, the combination of early snowmelt and above-average heat created a double compounding effect. Soils that would normally retain moisture until summer are now exposed to intensive apparative demand, stripping them dry well before the peak irrigation and growing season. Across the southeast, florid parched landscapes experience similar dynamics. Dense vegetation, once saturated, loses water rapidly, increasing local temperatures and reducing humidity, which suppresses cloud formation and rainfall potential. This feedback loop is further reinforced by stressed plants closing their stomata to conserve water, reducing transpiration, and in turn limiting atmospheric moisture that might have encouraged precipitation. Agricultural impacts are immediate. Wheat fields, citrus groves, and pasture lands already under stress are facing terminal soil moisture deficits, locking in yield reductions before the main growing season has begun. Reservoirs and aquifers cannot compensate because evaporation from surface water and soil accelerates, and inflows are diminished by depleted snowpack and suppressed rainfall. Even wildfire risk is magnified. Higher temperatures desiccate vegetation faster, increasing fuel loads across ecosystems unaccustomed to these conditions. In short, heat acts as a multiplier, transforming existing drought into a more severe and self-reinforcing event. By the time the expected Super El Niño begins to exert its influence, the system is already primed for catastrophic outcomes. Soils, vegetation, water infrastructure, and energy grids are all operating under extreme stress. Understanding the heat multiplier is essential to grasp why 2026 is not merely another dry year but represents a fundamental shift in baseline risk. The pre-trigger drought has already been amplified by thermal conditions, meaning that the eventual El Niño forcing will layer additional stress atop a system already exceeding historical extremes, creating a compound crisis that unfolds faster and more intensely than any previous drought in recorded American history. Chapter 6, Soil as an Active Driver. Drought is often conceptualized as a simple deficit. Less rain, soil rise, plants suffer. But 2026 has demonstrated that soil is not a passive receiver, it is an active driver of drought dynamics. When moisture in the soil drops below critical thresholds, it changes how incoming solar energy is partitioned. Normally, wet soils and healthy vegetation channel energy into evapotranspiration, a cooling process that moderates surface temperatures, maintains humidity, and contributes moisture to the lower atmosphere. As soils dry, this pathway collapses. Energy is redirected into sensible heat, warming the ground and the boundary layer above, reducing relative humidity, suppressing cloud formation, and decreasing the likelihood of rainfall. Vegetation under extreme water stress closes stomata to conserve water, further cutting the supply of moisture to the atmosphere, reinforcing drying in a self-perpetuating loop. This effect scales across landscapes. A single field under stress influences local microclimates, a watershed under stress modifies regional humidity, and an entire drought-affected continent produces measurable suppression of moisture recycling over thousands of square kilometers. In 2026, the soil-atmosphere feedback was operating at unprecedented intensity. In the southwestern southern plains, soil deficits that accumulated over years compounded the pre-trigger drought, ensuring that crop failures, reservoir drawdowns, and wildfire risks were locked in before any super El Niño forcing arrived. Feedbacks extend beyond water cycling. Stressed and dying vegetation releases carbon, reduces albedo, and removes natural cooling, which further accelerates warming and drying. Fire amplifies these dynamics, burning live and dead biomass, creating hydrophobic soil layers, reducing infiltration, and altering watershed hydrology for years. Unlike past droughts, where precipitation deficits were the primary driver, in 2026 the soil itself became a co-author of the drought, dictating its pace and intensity. Farmers, water managers, and emergency planners are confronting a system where the soil has already set the stage for crop loss, energy strain, and it misses us, and ecological stress, independent of the precipitation that is yet to come. Understanding this active role of soil explains why the pre-trigger drought accelerated more rapidly than historical analogs and why the impacts are compounding across multiple sectors simultaneously. In essence, the ground beneath us is no longer passive. It participates in the unfolding catastrophe, amplifying extremes and ensuring that when the full climate forcing arrives, the system will already be operating at the edge of collapse. Chapter 7, The Mega Drought Continuation. The drought of 2026 is not an isolated anomaly. It is the latest chapter in a multi-decade mega drought that has been quietly intensifying across the American Southwest. Tree ring reconstructions extending back 200 years revealed that the 22-year period from 2000 to 2021 was the driest stretch in over a millennia, surpassing even the prolonged droughts of the 1500 seconds and 1600 seconds. Approximately 42% of that drying was attributable to anthropogenic warming, illustrating that human-driven climate change has compounded the natural variability of the region. What is unfolding now is a continuation and amplification of this long-term pattern. The spring of 2026 does not mark the beginning of the drought. It represents a system already stressed, entering an accelerated phase that intersects with unusually high temperatures, depleted snowpack, and suppressed rainfall patterns. Reservoirs designed to buffer water variability are nearing critical thresholds, soil moisture is reaching record lows, and vegetation across arid and semi-arid ecosystems is experiencing stress levels rarely documented in the instrumental record. Agricultural systems, particularly wheat and winter crops, are encountering conditions where the pre-existing soil moisture deficit has already locked in potential yield losses, a phenomenon known as the invisible crop failure phase. Meanwhile, Heat amplification magnifies these impacts. Higher temperatures increase evaporative demand, drawing even more moisture from already stressed soils, creating a feedback loop that accelerates ecosystem and human vulnerability. The historical analogues, such as the Dust Bowl of the 1930 seconds or the mega-droughts of the 1500 seconds, provide context for duration and severity, but fail to capture the compounding effects of modern heat amplification, depleted water infrastructure, and interconnected agriculture and energy systems. In essence, the pre-trigger drought of 2026 is superimposed on a long-term baseline that is already far from normal, which explains why the severity of impacts, crop stress, reservoir depletion, and livestock pressure is disproportionate to the precipitation deficit alone. Understanding this continuation of the mega-drought is critical. It frames 2026 not as a temporary anomaly, but as a systemic shift, one in which existing vulnerabilities have been preloaded for catastrophe, and where the upcoming Super El Niño could add yet another layer of intensity to an already overstressed system. The mega-drought's persistence emphasizes that the U.S. is no longer responding to short-term fluctuations but to a long-duration structural shift, where conventional historical benchmarks are insufficient to predict outcomes. Chapter 8: Agriculture Collapse Signals. Drought impacts become tangible through the lens of agriculture, where soil moisture deficits translate directly into crop failure and economic strain. In Kansas, the nation's winter wheat benchmark, early April 2026 revealed a stark reality. Only 31% of the winter wheat crop was rated good to excellent, with the majority of fields rated poor or very poor or very poor. These conditions are a direct consequence of the pre-triggered drought compounded by the long-term mega-drought, heat amplification, and depleted snowpack. Crop establishment and growth have been stunted weeks ahead of historical norms, locking in yield reductions that cannot be recovered by subsequent rainfall. Farmers are facing decisions that are as much economic as they are agrimonic, whether to irrigate from the Orgale or La Aquifer, whose water table has declined by up to 50% in some areas, or to abandon failing crops altogether. The invisible crop failure phase is particularly insidious. Satellites may still show green vegetation, markets may not yet price in mosses, but soil probes and farmers' assessments already indicate irreversible stress. These localized failures ripple outward through commodity markets, elevating wheat prices domestically and internationally, with acute effects on import-dependent nations in sub-Saharan Africa, South Asia, and the Middle East. The pre-trigger drought thus acts as a structural shock to global food systems, a crisis already in motion before El Niño or other climate forcings fully materialize. Beyond crops, livestock serves as another signal of agricultural vulnerability. Cattle herds are being liquidated in response to feed shortages, driving short-term price volatility and long-term supply reductions that will echo for years. In 2026, approximately 60% of the U.S. cattle herd resides in drought-affected areas, magnifying the impact of forced sales and disrupting national beef supply chains. These early signals from crops and livestock reveal a cascading reality. The pre-trigger drought has not only stressed the land, but has already set economic and ecological feedbacks in motion. Understanding these agricultural collapse signals demonstrates how a single environmental anomaly propagates through interconnected systems, locking in consequences long before the climate driver, El Niño, fully manifests, underscoring the unprecedented nature of the 2026 drought crisis. Chapter 9: The 70-year cattle signal. The livestock sector offers a stark, tangible indicator of drought severity, often revealing the economic and ecological consequences of water scarcity before they appear in other metrics. In January 2026, the USDA reported a total U.S. cattle and calf inventory of Itexus 2 million head, the lowest level since 1952. This decline is directly tied to the pre-trigger drought. Pastures have failed, hay production has plummeted, and feeding costs have skyrocketed. Ranchers are forced into liquidation cycles, selling calves, cows, and bulls they can no longer sustain. Unlike crops, livestock cannot be replanted or regrown within a season. Once breeding stock is sold, the full recovery of herds requires 3 to 5 years, even under optimal conditions. This delay means that the economic and production impacts of the 2026 drought are locked in long before any visible El Niño-induced rainfall arrives. Approximately 60% of the U.S. herd resides in regions simultaneously experiencing severe drought, amplifying the nationwide structural stress. As ranchers offload animals, market dynamics create a cascade. A temporary glut depresses prices, followed by multi-year spikes as herds rebuild. The implications extend beyond domestic consumption. The United States is a major beef exporter. Disruptions in supply influence global markets, disproportionately affecting populations already spending the largest share of income on food. This 74-year cattle signal, therefore, is more than a historical curiosity. It is a predictive measure of both immediate and delayed economic consequences. It shows how pre-trigger drought conditions can initiate long-term cascading effects, locking in stress across agriculture, energy, and global food systems before the primary climate driver, El Niño, has even fully manifested. By monitoring livestock responses, we gain insight into how early systemic vulnerabilities compound, highlighting the interdependence of environmental stresses and human decision-making. The drought's effects, visible in cattle numbers, illustrate that when multiple systems fail concurrently, recovery is slow, uncertain, and economically costly. The pre-trigger signal from livestock emphasizes a central point. By the time conventional metrics indicate extreme drought, the structural damage has often already been determined, creating an invisible lag between impact and observation that will shape markets, food security, and ecosystem resilience for years to come. Chapter 10. The Colorado River Edge. Few systems illustrate the cascading vulnerability of the 26 drought better than the Colorado River Basin. Glen Canyon Dam, a 100-meter concrete barrier straddling Utah and Arizona, and its reservoir, Lake Powell, are foundational for water storage, hydroelectric generation, and regional agricultural irrigation. As of spring 2026, Lake Powell held roughly 23% of its full capacity, exposing the iconic bath to brings in signaling a reserve or approaching critical thresholds. Hydroelectric power generation is directly proportional to water column height, below the minimum power pool elevation of 490 feet. Turbines cannot operate efficiently or at all. The combination of record low snowpack, early snowmelt, and above-average spring temperatures ensures that inflows are insufficient to restore the reservoir to functional levels, even under optimistic precipitation projections. Downstream, Lake Mead mirrors this stress at roughly 30% capacity, triggering mandatory cutbacks under the Colorado River Compact framework. These cutbacks affect millions of urban and agricultural users in Arizona, Nevada, and Mexico, highlighting the interdependence of water storage, energy production, and human consumption. Beyond hydropower, reduced flows limit irrigation for vast agricultural lands, affecting crops already stressed by soil moisture deficits, heat amplification, and prolonged drought conditions. Water managers, planners, and municipal authorities are forced to make preemptive allocations, balancing immediate consumption against long-term sustainability, a task complicated by the unprecedented timing of the drought pre-trigger. Unlike historical droughts, where reservoir levels decline gradually and relief is often possible through seasonal precipitation, the 2026 pre-trigger scenario places both Lake Powell and Lake Mead on a trajectory toward threshold system failure, where recovery would require multiple years of above-average inflows. The Colorado River Edge demonstrates how interconnected infrastructure, environmental stress, and human systems amplify drought impacts. By understanding the pre-trigger dynamics here, it becomes clear that the year's water availability, energy production, and agricultural security have already been constrained well before the anticipated El Niño. emphasizing that the structural consequences of the drought were decided months in advance, long before the climate forcing fully arrived. Chapter 11. Fire Season Acceleration. The pre-triggered drought of 2026 is not only a silent thief of water, it is a visible and immediate threat through the acceleration of wildfire activity. By early May, approximately 1.8 million acres had already burned across the United States, representing 231% above the 10-year average for this period. This early surge is unprecedented. In a normal year, such a level of activity would correspond to the peak of midsummer fire season. The combination of heat amplification, depleted soil moisture, and pre-dried vegetation has created a volatile fuel environment, extending the geographic reach of fire danger beyond the traditional arid west into the southeast, including Florida, Georgia, and Alabama. Wildfire management infrastructure is not calibrated for this expanded scale and early timing, meaning air tankers, hotshot crews, and suppression equipment are committed earlier than usual, leaving fewer resources available for the season's historically busiest months. Atmospheric conditions, measured by the Evaporative Demand Drought Index, EDI, show historically extreme moisture-sucking capacity, causing the vegetation to desiccate faster than expected, even where precipitation deficits alone would not have indicated such high fire risk. High EDI values led to rapid fire spread, extreme flame lengths, and pyrocumulonimbus development, allowing embers to travel far ahead of the main front. The fires themselves create feedback loops that further intensify drought. Intense heat forms hydrophobic soil layers, reducing water infiltration and groundwater recharge, while burning removes vegetation that moderates surface temperature and contributes to local humidity. As a result, post-fire landscapes contribute to accelerated evaporation, reduced precipitation efficiency, and greater vulnerability to subsequent fires. These simultaneous feedbacks, drought-creating fire, fire-deepening drought, are amplified across thousands of square kilometers, producing a compound hazard that outpaces human management capacity. In 2026, the fire season is pre-triggering economic and ecological damage. Forests and rangelands are losing biomass, carbon emissions are increasing, and local communities face amplified exposure to smoke, property loss, and infrastructure strain. The early onset and intensity of wildfire illustrate that the pre-triggered drought is not a passive condition, it is actively reshaping ecosystems, energy consumption patterns, and human risk landscapes long before the anticipated El Niño could add additional forcing. Understanding fire season acceleration provides a clear example of how pre-existing drought conditions interact with vegetation heat and atmospheric demand to generate crises whose full consequences are realized over months and years. Chapter 12. Planetary Synchronization. The drought gripping the United States in 2026 is not an isolated event. It is part of a planetary-scale climate alignment that links atmospheric patterns across continents. Teleconnection systems, large-scale atmospheric bridges connecting distant regions, demonstrate that the same dynamics producing pre-trigger drought in North America are mirrored globally. For example, India's 2026 monsoon forecasts predict rainfall at only 92% of long-period averages, affecting 1 billion people who rely on monsoon-fed agriculture. Simultaneously, Indonesia is experiencing an earlier dry season, compressing planting and harvesting schedules, while Southern Africa faces a humanitarian drought crisis, already prompting international emergency responses. These are not coincidental or regionally isolated phenomena. They reflect a global redistribution of heat, moisture, and atmospheric circulation, in alignment with the slowly developing El Niño signal. The synchronization demonstrates that pre-trigger drought in the U.S. is linked to larger teleconnections in the Pacific and Atlantic, showing how local water stress is inseparable from global climate dynamics. Crop failures, reservoir depletion, and energy stress in one region interact indirectly with other systems worldwide through trade, food prices, and resource allocation. For instance, the reduction in U.S. Wheat and beef supply can amplify food insecurity in import-dependent regions simultaneously experiencing their own climate stresses. The planetary context highlights that pre-trigger conditions are not just local anomalies, but components of interconnected global vulnerability, emphasizing that the timing and sequencing of climate events matter. The U.S. is already stressed before El Niño reaches its peak, while other continents experience parallel deficits. Understanding this synchronization is critical for interpreting global risk. Early drought impacts in North America are amplified by simultaneous pressures elsewhere, limiting conventional mitigation or import-based relief options. In this pre-trigger phase, the systemic vulnerabilities of agriculture, water, and energy are compounded not only by domestic conditions, but also by synchronous stress across multiple continents, revealing the truly unprecedented nature of the 2026 drought and the necessity of examining both local and global feedbacks to anticipate cascading impacts. Chapter 13. The El Niño Paradox. El Niño, a periodic warming of the central and eastern tropical Pacific Ocean, is widely recognized as a major driver of global weather anomalies. Historically, strong El Niño events have reshuffled precipitation patterns, bringing drought relief to some regions while intensifying stress in others. In 2026, models forecast the development of a potential super El Niño, with sea surface temperature anomalies projected above 3°C in the central Pacific. Yet the paradox lies in timing. Drought conditions are occurring before the El Niño peak, challenging conventional assumptions that precipitation deficits follow tropical forcing. Across the southern tier of the United States, rainfall is already insufficient, snowpack is depleted, and soils are dry. In the southeast, the Bermuda High suppresses cloud formation and maintains record-level soil moisture deficits. The super El Niño may eventually alter storm tracks, increasing rainfall in some areas while deepening drought in others. But the baseline drought conditions have already been established, meaning the additional forcing will layer atop a system operating at historical extremes. This inversion of expected causality, where impacts precede the trigger, reveals a structural vulnerability. The U.S. is entering the El Niño phase with soils, vegetation, reservoirs, and energy systems preloaded for crisis. Historical events, such as the 1997-1998 Super El Niño, show that maximum drought impacts typically lag peak ocean warming by 6-12 months. Yet in 2026, soil moisture deficits, reservoir depletion, and wildfire activity have already exceeded prior records. The El Niño paradox underscores the compounding nature of pre-trigger conditions, while models anticipate atmospheric response. The systemic stress is already in motion, raising urgent questions about how much additional impact the tropical forcing can produce and how unprepared infrastructure and ecosystems are for a secondary shock. For agriculture, energy, and water management, this pre-existing baseline means decisions and allocations are being made in a context far beyond historical experience, highlighting that the drought severity is amplified not just by El Niño itself, but by the timing and pre-existing system state, the combination without modern analog. Chapter 14. The 1877-1878 analog. To understand the potential implications of 2026's pre-trigger drought, historical analogs provide insight, though they are incomplete. The 1877-1878 El Niño event, the most powerful of the 19th century, reorganized global precipitation patterns and contributed to simultaneous crop failures across China, India, Brazil, and parts of Africa, leading to the Great Famine that killed an estimated 30-50 million people. While modern infrastructure, early warning systems, and global trade have dramatically improved resilience, the mechanism remains instructive. A strong tropical Pacific forcing can synchronize drought and stress across multiple agricultural regions simultaneously, overwhelming local adaptive capacity. In 2026, we are witnessing a structural parallel. Multiple major U.S. agricultural regions, the southern plains, southwest, and southeast, are already experiencing severe drought before El Niño's full development. The timing amplifies the compound risk. Just as 1877, 1878 demonstrated the effects of synchronized multi-regional stress, the pre-trigger conditions in 2026 suggest that local systems are already operating near or beyond thresholds. Unlike 19th century societies, the U.S. benefits from advanced monitoring, irrigation, and emergency response, yet these systems were not designed for continental scale. Preloaded drought stress intersecting with a developing super El Niño. 1878 analog illuminates the vulnerability inherent in synchronized climate forcing. But in 2026, the U.S. drought is layered atop decades of warming, depleted reservoirs, and pre-existing mega-drought conditions, creating a scenario that historical precedent can guide, but not fully explain. Understanding this analog emphasizes the unprecedented convergence of stressors, highlighting that timing, system preconditioning, and feedback loops matter as much as the magnitude of El Niño itself. It sets the stage for evaluating not just potential rainfall impacts, but systemic responses across agriculture, water, energy, and fire management, revealing the true novelty and severity of the pre-trigger drought event. Chapter 15. The missing relief mechanism in a typical year. Droughts are eventually interrupted by natural relief mechanisms. For the southeastern United States, one of the most reliable is the tropical storm and hurricane season. Hurricanes and tropical systems moving inland from the Gulf of Mexico or Atlantic Ocean deliver enormous quantities of precipitation in short periods, often replenishing depleted soil moisture, recharging reservoirs, and suppressing wildfire activity. Yet in 2026, the pre-trigger drought has exposed a critical vulnerability. The very El Niño event that may later intensify drought risk is simultaneously suppressing the formation of tropical storms over the Atlantic. Strong El Niño conditions increase upper-level wind shear, which tears apart developing storms before they can mature. As a result, the principal relief mechanism for the southeast is weakened before it is even needed. The implications are stark. Even if rainfall were to occur, the combination of hydrophobic soils from previous fires, depleted vegetation, and preloaded heat amplification reduces the capacity of precipitation to restore water availability. This creates a closed-loop system where atmospheric patterns maintain drought, the soil and vegetation amplify it, and the expected hurricane relief is less likely to arrive. Unlike historical droughts, where eventual recovery occurred naturally over time, the 2026 pre-trigger drought operates under conditions where the relief mechanisms themselves are compromised, extending the duration and severity of water stress across multiple sectors. Reservoirs cannot fully recharge, crops cannot recover, and the likelihood of cascading failures increases. The system is locked in dry mode, reinforced by multiple reinforcing feedbacks that operate simultaneously. The pattern lock prevents rainfall. It amplifies soil drying, soil and vegetation feedback suppress precipitation locally, and El Niño suppresses the tropical storm season. These overlapping mechanisms demonstrate that the pre-trigger drought is not simply a delayed weather event, it is a structurally self-sustaining phenomenon, where natural intervention that historically mitigated drought is either delayed or actively suppressed. The missing relief mechanism highlights the fragility of existing infrastructure and ecosystems in the face of unprecedented timing, showing that in 2026, the United States is experiencing a drought scenario unlike any other in the instrumental record. Chapter 16. The narrative failure. Despite the magnitude of the 2026 pre-trigger drought, there exists a gap between the data and public awareness. Agricultural reports, water management updates, wildfire alerts, and commodity market indicators have documented extreme conditions. Yet the integrated story of a continental scale, preloaded drought has largely failed to penetrate the national conversation. This is a phenomenon known as narrative failure, where the complexity and slow progression of a disaster prevent coherent storytelling and public perception. Unlike hurricanes, earthquakes, or floods, droughts do not have a singular event horizon. Their accumulation is gradual, almost imperceptible on a day-to-day basis. The Palmer Drought Severity Index can cross extreme thresholds without noticeable change in the landscape. Satellite imagery may still show vegetation, and rivers may appear deceptively full. Media coverage, fragmented across agricultural, regional, and fire-specific outlets, highlights individual aspects but rarely conveys the systemic, interconnected nature of the crisis. The human brain, adapted to respond to acute dramatic events, struggles to prioritize slow-moving catastrophes. As a result, institutions, policymakers, and individuals may underestimate urgency, delaying proactive adaptation and mitigation measures. The narrative failure in 2026 amplifies risk. Decisions are being made in partial context, reinforcing the invisibility of cumulative damage until thresholds are crossed. This failure is compounded by overlapping sectors: agriculture, water management, energy, and wildfire preparedness, each reporting extremes independently, yet none presenting a unified systemic story. Understanding narrative failure is critical to assessing pre-triggered drought dynamics. It explains why public perception lags behind observable data, why markets may not fully price in losses, and why societal responses are constrained. In 2026, the drought is not only physically unprecedented but also cognitively invisible, allowing systemic vulnerabilities to deepen before the expected El Niño forcing fully arrives, demonstrating that comprehension and education are as essential to risk mitigation as the data itself. Chapter 17: The Conspiracy Layer. When an event of this scale unfolds quietly, human instinct searches for intentionality. Online discussions about the 2026 pre-triggered drought frequently invoke conspiratorial explanations: HAARP, cloud seeding, solar cycles, and chemtrails, suggesting that someone or some system is deliberately manipulating weather patterns. HAARP, the High-Frequency Active Auroral Research Program in Alaska, transmits roughly 3.6 megawatts of energy into the ionosphere, sufficient for studying ionospheric physics, but astronomically insufficient to influence continental scale weather, which involves energy transfers on the order of 10-19 joules. Cloud seeding, while scientifically documented, requires existing clouds with sufficient moisture. The pre-triggered drought atmosphere is dry from the top down, leaving no viable conditions for precipitation enhancement. Solar cycle arguments similarly fail under scrutiny. The current sun activity remains within normal bounds, and irradiance changes are a fraction of a percent, insufficient to explain massive regional droughts. Chemtrail theories proposing that aircraft disperse chemicals to suppress rainfall ignore scale limitations. The volume of material required to influence the atmosphere across an entire continent would be detectable and incompatible with observed flight patterns and atmospheric chemistry data. These conspiratorial narratives share a common appeal. They imply control and intentionality, but they do not match the physics or observational evidence. The drought's actual explanation resides in observable, measurable processes: the persistent Rossby wave configuration, the westward extension of the Bermuda High, heat amplification, and soil-atmosphere feedbacks, all operating in accordance with thermodynamics and long-term climatic trends. The system behaves in ways that feel unfamiliar because it is already operating outside historical norms, exceeding pre-existing baselines, not because a hidden actor is manipulating it. While conspiratorial thinking is psychologically comforting, suggesting that a switch could be flipped to stop the drought, the reality is that the system is governed by natural processes that have been pushed to extremes through decades of warming and structural vulnerability. Understanding the physics behind the 26 pre-triggered drought emphasizes that its severity is not the product of manipulation, but the result of compounding feedbacks in an interconnected climate system, highlighting the scale, energy, and complexity required to shape continental weather, forces far beyond human technological capacity. Chapter 18: The Ceiling Problem. Every major drought in U.S. history offers benchmarks, patterns of impact, warning signs, and expected outcomes, but 2026 presents a ceiling problem. There is no precedent that fully contains the observed combination of stressors. Comparing to the Dust Bowl of the 1930 seconds, the Palmer Drought Severity Index values of March 20,267, 85, and April 2026 are close to the worst recorded months of 1934. Yet they occur in a warmer, more interconnected climate with amplified evaporative demand. Unlike historical events, the drought now unfolds atop a multi-decade mega-drought in the southwest, depleted reservoirs, and extreme pre-trigger conditions across the southeast and western U.S. The combination of heat amplification, pattern lock, soil feedback loops, and pre-existing water stress creates a systemic ceiling that historical analogs cannot fully predict. The magnitude of these interacting factors means that outcomes could exceed prior extreme events or deviate entirely from them, producing nonlinear, compounding impacts across agriculture, energy, water management, and wildfire risk. This ceiling problem also underscores the limitations of predictive models. While climate simulations can estimate average outcomes and general trends, the upper tail of extreme possibilities is less certain, particularly when multiple reinforcing feedbacks operate simultaneously. Each additional factor, soil dryness, heat, reservoir depletion, fire risk, or El Niño forcing, adds a layer of complexity that amplifies systemic vulnerability. In 2026, the pre-trigger drought demonstrates that extreme events are no longer isolated deviations but can push systems to their operational limits, challenging assumptions about what is possible, what is survivable, and what constitutes an exceptional event. Recognizing this ceiling problem is essential. It frames 2026 not just as a record-breaking drought, but as a scenario where upper bound uncertainty is unprecedented, reinforcing the urgency of understanding, monitoring, and adapting to the cascading impacts before the system reaches an unrecoverable state. Chapter 19: Compound Systems and Interconnected Failures. The 2026 pre-trigger drought is not a singular environmental anomaly. It is a network of interconnected systems failing simultaneously, producing cascading consequences that amplify across agriculture, water management, energy management, and ecosystems. Crops under extreme soil moisture deficits cannot reach full yield potential, locking in food supply reductions that ripple through domestic and global markets. Livestock herds, already reduced to 74-year lows, face forced liquidation, creating multi-year supply disruptions. Reservoirs like Lake Powell and Lake Mead, critical for irrigation and hydroelectric power, are approaching minimum operational thresholds, threatening energy generation for millions of households and adding stress to regional electrical grids during peak summer demand. Drought impacts amplify fire risk. Desiccated vegetation serves as fuel, high temperatures intensify ignition probability, and wildfires further alter soil properties, reducing infiltration and long-term water retention. The interactions between these systems are not sequential. They occur simultaneously, with feedback loops that magnify the effects of each stressor. For example, reduced reservoir levels increase irrigation demand, which accelerates aquifer depletion, in turn lowering soil moisture, increasing crop stress, and worsening fire vulnerability. Meanwhile, vegetation mortality decreases transpiration, suppressing local cloud formation, reinforcing heat amplification, and perpetuating the drought. These compound systems demonstrate that the pre-trigger drought is not simply a function of rainfall deficit, but of structural vulnerability built over decades. Warming, snowpack loss, multi-year megadroughts, and human water management practices all contribute to a system where cascading failures become inevitable. The simultaneous pressure across multiple sectors explains why the 2026 drought surpasses any historical analog. It is not just extreme in one metric or one region, but systemically extreme, affecting every interdependent element at once. The lesson is clear: a pre-trigger event of this scale has already determined downstream consequences. Even if the Super El Niño arrives as predicted, it will layer additional stress onto a system that is already operating near failure thresholds. Understanding these interconnected failures underscores the importance of anticipatory management and multi-sector coordination, as reactive measures will be insufficient when multiple systems interact to amplify drought impacts across a continent. Chapter 20. The final frame, returning to the scale of the 2026 pre-triggered drought, reveals a scenario that combines historical extremes with unprecedented convergence. Over 60% of the contiguous United States is in drought, nearly half classified as severe to exceptional. Florida, a state defined by humidity and water abundance, experiences near total drought coverage, while 8 western states record all-time lows in snowpack. Cattle herds are at the lowest levels in 74 years, winter wheat and other crops are collapsing under soil moisture deficits, and reservoirs that were engineered as buffers are approaching thresholds never intended to be breached. Fires are running far ahead of schedule, while hurricane projections indicate a below-average season, removing one of the few mechanisms capable of interrupting drought in the southeast. The critical insight lies in timing. All of this is occurring before the climate-forcing event, El Niño, has fully materialized. This pre-trigger scenario illustrates that drought severity, ecosystem stress, and economic consequences are already in motion, independent of the anticipated tropical forcing. The United States is operating on a shifted baseline, where historical assumptions about sequence, causality, and resilience no longer hold. The impacts are locked in across interconnected systems: agriculture, water infrastructure, energy generation, wildfire management, and ecological networks are simultaneously stressed, creating feedback loops that reinforce drought intensity. Unlike prior extreme events, the 2026 drought demonstrates that impacts can precede the trigger, reshaping risk assessments and exposing vulnerabilities before warnings and mitigation efforts can be fully mobilized. This final frame emphasizes that understanding pre-trigger dynamics is essential. The drought is not merely a meteorological record, but a structural inflection point with cascading consequences that will unfold over months and years. Observing and analyzing the data now is the closest opportunity to anticipate outcomes, guide resource management, and adapt infrastructure to a system whose limits have already been tested, revealing the extraordinary complexity and unprecedented scale of the 2026 continental drought. Chapter 21. The shadow of global interdependence. The United States does not experience drought in isolation. The 2026 pre-trigger drought occurs against a backdrop of globally interconnected agricultural and climate systems, meaning local water scarcity has immediate international ramifications. U.S. wheat, corn, and beef exports play a critical role in global food supply chains. Reductions in these commodities reverberate across markets, disproportionately affecting import-dependent regions in sub-Saharan Africa, South Asia, and the Middle East. Early spring 2026 soil deficits, crop failures, and livestock liquidation set in motion a series of economic adjustments. Rising global grain prices, altered trade flows, and increased food insecurity in regions already vulnerable to climatic stress. Simultaneously, teleconnection patterns link atmospheric dynamics across continents. The same Rossby wave anomalies on Pacific teleconnections driving pre-trigger drought in the U.S. are mirrored by below-average monsoon rainfall in India, an early dry season in Indonesia, compressing planting and harvest cycles and straining local food systems. Southern Africa experiences humanitarian drought conditions, forcing emergency aid interventions, while crop failures propagate risk through global commodity markets. This planetary perspective demonstrates that the U.S. pre-trigger drought is part of a synchronized global stress event where multiple agricultural regions are simultaneously under pressure. The convergence of climatic, ecological, and economic factors amplifies the consequences of local drought conditions, creating feedback loops that propagate risk worldwide. What occurs in the southern plains or southwest today directly influences food security, trade decisions, and policy measures thousands of miles away. In effect, the pre-trigger drought acts as a planetary-scale experiment in system vulnerability, highlighting the interdependence of climate, agriculture, and economic stability. Understanding these global linkages is essential. The drought's impacts are not contained within you. Borders, and anticipating the cascading consequences requires recognizing that the pre-trigger phase already shapes international resilience, emergency response, and market stability long before the full El Niño forcing arrives. Chapter 22: The snowpack collapse as a precursor. While global interdependence defines the broader context, the Western United States demonstrates how local environmental thresholds amplify the pre-trigger drought. Snowpack, the natural reservoir in the Rocky Mountains, Sierra Nevada, and Cascades, serves as the backbone of water supply for tens of millions of Americans. By April 1, 2026, snowpack levels across 8 western states were all-time record lows, with Oregon at just 12% of the historical median. Colorado and Utah ranging between 20–30%, and over 75% of snow-tel monitoring sites reporting complete melt more than a month early. Snow water equivalent (SWE) measurements reveal not just depth, but the total water content, which determines inflow for rivers, reservoirs, and aquifers during the dry season. The early melt pulses water into rivers too quickly for reservoirs to capture efficiently, leaving surface water unavailable for the peak summer demand. In the Colorado River Basin, temperatures were anomalously high, up to 37 F above average, further converting potential snowpack into immediate runoff and evaporative loss. This combination of absent snowpack and heat amplification sets the stage for cascading failures across water, energy, and agriculture. Reservoirs like Lake Powell and Lake Mead, already depleted, cannot store the diminished runoff effectively, threatening hydroelectric generation and irrigation schedules simultaneously. This pre-trigger snowpack collapse locks in water scarcity for the entire season, creating structural deficits independent of subsequent precipitation or tropical forcing. The early snowmelt also exacerbates wildfire risk. Dry soils and exposed vegetation drive faster under heat amplification, creating additional fuel for fires. Understanding the snowpack collapse as a precursor emphasizes that the 2026 drought is structurally encoded months before the primary El Niño forcing, illustrating how missing natural reservoirs dictate the trajectory of environmental and economic impacts, and why pre-trigger conditions are already shaping systemic vulnerabilities across the American West. Chapter 23: Agriculture Under Pressure. The 2026 pre-trigger drought is reshaping American agriculture in real time, and its impacts are already measurable in the fields, pastures, and farms across the nation. Winter wheat, a staple crop concentrated in the southern and central plains, faces conditions that lock in yield reductions before the growing season is fully underway. Soil moisture measurements indicate extreme deficits, often in the lowest 5–10% of historical ranges, preventing germination, limiting vegetative growth, and creating what researchers call the invisible crop failure phase, where plants have already failed, yet visual signs and market signals lag behind. Farmers confront stark economic decisions: irrigate using the Ogale or aquifer, risking accelerated groundwater depletion, or abandon failing fields entirely, minimizing short-term losses at the expense of long-term productivity. The pre-trigger drought thus generates structural economic consequences, with wheat yields projected to fall up to 31% below the 5-year average in the southern plains. Livestock operations face parallel stresses. Cattle herds located in drought-affected pastures are subject to forced liquidation, compounding pressure on both domestic and international markets. U.S. beef exports are critical to global food supply chains. Reductions in herd size amplify commodity price volatility and can worsen food insecurity in import-dependent regions, such as sub-Saharan Africa and South Asia. The convergence of crop failure, water scarcity, and this stock pressure demonstrates that agriculture is both a victim and an amplifier of the pre-trigger drought. Irrigation demand, reduced snowpack inflows, and heat amplification collectively increase stress on soil and plants, accelerating water loss and ensuring that early season impacts set the stage for the entire production cycle. By analyzing these dynamics, it becomes clear that the 2026 drought does not operate as isolated events, but through interconnected mechanisms, where soil, vegetation, water infrastructure, and human decision-making interact to lock in consequences months before the full climate forcing arrives. Understanding these pre-trigger agricultural signals is crucial. They provide an early warning system, revealing that structural failure has begun long before visual cues, market responses, or weather extremes confirm the severity of the event. Chapter 24. Cattle and livestock feedbacks in parallel with crop impacts. Livestock in 2026 serves as a clear barometer of drought severity, revealing systemic vulnerabilities that extend well beyond agriculture. The total U.S. cattle and calf inventory dropped to 2 million head, the lowest since 1952, illustrating how drought directly drives herd management decisions. When pastures fail and feed becomes scarce, ranchers implement liquidation cycles, selling calves, cows, and bulls to offset escalating costs. Unlike crops, livestock cannot be replanted. Recovery of herds requires 3 to 5 years, making pre-trigger conditions an early determinant of long-term supply. Approximately 60% of the U.S. cattle herd resides in drought-affected areas, amplifying the structural impact of forced sales and reducing resilience to future climate events. The resulting market effects are compounded. Initial oversupply depresses prices temporarily, while multi-year herd rebuilding drives subsequent price spikes, influencing both domestic consumers and international importers. Cattle liquidation interacts with other drought feedbacks. Decreased grazing pressure may slow soil moisture loss locally, but the broader effect is a reduction in ecosystem resilience as pastures and feed systems fail to recover quickly. The timing of herd reductions before El Niño's peak demonstrates that the economic and ecological consequences of the pre-trigger drought are already baked in, independent of subsequent climate forcing. Moreover, this signal highlights the interdependence of agricultural systems as livestock supply adjusts, feed demand, water usage, and grazing patterns shift, creating cascading effects across local and regional economies. In essence, the 2026 drought is self-propagating. Livestock not only responds to environmental stress, but also contributes to the broader feedback loops that amplify systemic vulnerability, confirming that pre-trigger conditions are already defining the trajectory of agricultural, economic, and ecological outcomes months before the full El Niño influence arrives. Chapter 25. Water infrastructure at the edge. The 2026 pre-trigger drought is testing the United States water infrastructure in ways unseen in modern history, highlighting the fragility of reservoirs, canals, aqueducts, and hydroelectric systems under extreme stress. Lake Powell, impounded by Glen Canyon Dam on the Utah-Arizona border, illustrates the systemic pressure facing the Colorado River Basin. By spring 2026, Lake Powell held only 23% of its full capacity, revealing the iconic bathtub that marks historical water levels and indicating the reservoir is dangerously close to the minimum power pool, below which turbines cannot generate electricity efficiently. Hydroelectric production in this region serves approximately 5 million households across multiple states, including Arizona, Nevada, Utah, and Colorado. Reduced water levels translate to reduced hydroelectric capacity, forcing energy managers to rely on alternative, often fossil fuel-based energy sources, increasing costs and carbon emissions. Meanwhile, Lake Mead downstream mirrors the same stress at approximately 30% of capacity, triggering cutbacks under the Colorado River Compact framework, affecting urban and agricultural users in Arizona, Nevada, and Mexico. These reservoirs operate as threshold systems, meaning their function changes dramatically when levels fall below critical thresholds. Above minimum capacity, they store water, generate electricity, and provide buffers against drought. Below these thresholds, they risk partial or complete functional collapse, with recovery requiring years of above-average inflows. The pre-trigger drought highlights a crucial structural vulnerability. Inflows are already compromised due to record low snowpack and early snowmelt across 8 western states, and above-average temperatures accelerate evaporation and runoff losses. Even robust infrastructure is rendered insufficient under these conditions, demonstrating that extreme drought is not simply a natural phenomenon, but a test of system design and operational flexibility. Agricultural irrigation, municipal water supplies, and industrial uses face simultaneous pressure, while planners must navigate allocations between competing users under extreme scarcity. Additionally, groundwater systems, such as the Ogeilola Aquifer, experience accelerated drawdown as surface water supplies are constrained. This reliance on depleted aquifers creates a long-term deficit, one that cannot be reversed in a single season, compounding vulnerability for future drought events. Hydrological modeling shows that pre-trigger conditions have already locked in substantial deficits, and any additional stress from the approaching Super El Niño will layer atop a system already operating at the limits of physical and operational capacity. Fire suppression systems, dependent on water resources for firefighting and landscape management, are also constrained, reducing the ability to mitigate early wildfire outbreaks, which in turn impacts soil stability and water infiltration. In sum, the 2026 pre-trigger drought demonstrates that water infrastructure is interdependent, sensitive, and already under extreme duress strain, with cascading impacts that extend to energy generation, agriculture, ecosystem health, and urban water security. Understanding the pre-trigger pressures highlights how close the system is to structural tipping points, and why proactive management and systemic resilience are critical to navigating a drought scenario that has already begun to exceed historical thresholds and infrastructure design expectations. Chapter 26: Early Fire Dynamics and Feedback Loops. Fire season in 2026 is unfolding months ahead of historical norms, with a pre-trigger drought setting unprecedented conditions for ignition, spread, and feedback. By early May, nearly 1.8 million acres had burned across the United States, a figure 231% above the 10-year average for this period. Unlike typical years, this is not an early season anomaly. It reflects a systemic alignment of drought, heat, and vegetation desiccation. The combination of extreme soil moisture deficits, above average temperatures, and pre-dried vegetation has created volatile fuel loads across both traditional wildfire regions and the western regions, not typically associated with large-scale fire, including the Southeast. Florida, Georgia, and Alabama now face the paradox of subtropical landscapes transformed into high-risk fire zones, where dense, normally water-saturated ecosystems burn faster and more intensely than arid western shrublands would under similar dryness. Fire management resources are under unprecedented strain. Air tankers, hotshot crews, and suppression equipment are committed earlier than usual, reducing availability for the historically peak months of summer. Fires themselves reinforce drought conditions through multiple feedback mechanisms. Intense heat from flames drives hydrophobic compounds into the soil, creating water-repellent surfaces that prevent precipitation from infiltrating, further reducing groundwater recharge. Vegetation removal exposes bare ground, increasing solar absorption, surface temperatures, and evaporation rates, while the absence of transpiring plants diminishes local humidity. These feedbacks operate simultaneously, creating a self-reinforcing loop. Drought intensifies fires, fires deepen drought, and both amplify heat exposure. High Evaporative Demand Drought Index, EDI, values confirm that the atmosphere is extracting moisture at historically extreme rates, desiccating the vegetation and creating conditions for rapid flame propagation, high-intensity burns, and pyrocumulonimbus formation capable of projecting embers miles ahead of the main fire front. In combination with pre-existing structural vulnerabilities, depleted reservoirs, low soil moisture, and weakened ecosystems, These early fire dynamics illustrate how compound feedback loops transform a pre-triggered drought into a multifaceted disaster. The timing is critical. Impacts are occurring before the anticipated El Niño forcing, meaning that once tropical Pacific warming interacts with these preconditioned landscapes, fire, drought, and heat feedbacks may accelerate further. Understanding early fire dynamics highlights that in 2026, drought, vegetation stress, and wildfire are not separate challenges but interconnected phenomena, each amplifying the other and ensuring that structural, ecological, and economic impacts are already locked in well before external climate drivers fully manifest. Chapter 27: Soil moisture feedbacks and thermal amplification. The 2026 pre-triggered drought illustrates the profound role of soil-atmosphere interactions in accelerating extreme conditions. Soil is not merely a passive recipient of precipitation, it actively shapes the climate response through a process known as soil moisture-atmosphere coupling. When soils reach critically low moisture levels, less incoming solar energy is partitioned into evapotranspiration, the process that normally cools the surface and maintains local humidity. Instead, energy is converted into sensible heat, warming the ground and the lowest layer of the atmosphere. This local heating amplifies evaporative demand, further depleting remaining moisture and suppressing cloud formation. Vegetation compounds this effect. Plants under water stress close stomata, limiting transpiration and reducing atmospheric moisture that might otherwise contribute to rainfall. Across landscapes, these processes scale from fields to watersheds, ultimately producing measurable reductions in atmospheric moisture, recycling over thousands of square kilometers. In 2026, this feedback was operating at unprecedented intensity, particularly in the southwestern southern plains, where soil deficits have been accumulating for years due to the ongoing megadrought. The pre-trigger drought is thus not merely a function of precipitation deficit, it is self-reinforcing, where soils and vegetation actively amplify dryness, even in the absence of additional forcing. Thermal amplification interacts with this feedback. Above average temperatures accelerate moisture loss, further stress crops, and heighten wildfire potential. The combination of dry soils, heat, and vegetation feedbacks produces a compound amplification, locking in agricultural stress, reservoir depletion, and fire vulnerability long before El Niño reaches peak influence. In practical terms, this means that the drought's intensity in 2026 cannot be mitigated solely through rainfall or irrigation, because the soil-atmosphere system has already created structural deficits. Recognizing the role of soil feedbacks and thermal amplification highlights why pre-trigger conditions are critical in determining the trajectory of extreme droughts. These self-reinforcing mechanisms ensure that impacts are already embedded in ecological, agricultural, and hydrological systems, creating a baseline of stress that will amplify subsequent climate events and compound risk across multiple sectors. Chapter 28: Heat-driven flash droughts. The 2026 pre-trigger drought also demonstrates the emergence of flash droughts, a phenomenon where conditions escalate from near normal to severe within weeks due to the interaction of heat, soil moisture, and atmospheric demand. Traditional droughts develop over months, allowing farmers, water managers, and ecosystems to adjust gradually. Flash droughts, however, compress the time scale of impact, intensifying stress before conventional monitoring systems detect the full severity. In early 2026, temperature anomalies across the western and southern United States were significantly above historical averages, enhancing evaporative demand and rapidly depleting already stressed soils. The combination of record low snowpack, pre-dried vegetation, and thermal amplification accelerated moisture loss, producing rapid onset conditions for crops, pastures, and forests. In the southern plains, wheat fields experienced terminal stress weeks ahead of planting windows, effectively locking in reduced yields and triggering irrigation from the Ogale or aquifer at unprecedented rates. Livestock faced simultaneous feed shortages, accelerating herd liquidation and compounding economic consequences. Flash droughts also increase wildfire potential. Rapid vegetation desiccation creates highly combustible fuel, enabling faster fire spread and higher intensity burns. Unlike slower developing droughts, the response window for mitigation is drastically shortened, meaning that water allocation decisions, emergency preparedness, and agricultural interventions must occur before stress becomes fully visible. In 2026, these conditions reflect pre-trigger amplification of drought impacts. The environment has already entered a high-stress state, independent of the super El Niño that forecasters predicted would intensify drought. The interaction of heat, soil moisture deficits, and rapid onset conditions illustrates that the system is nonlinear and self-reinforcing, with the timing and intensity of stress determined as much by internal feedbacks as by precipitation anomalies. Recognizing the role of flash drought dynamics provides insight into how pre-trigger conditions can lock in ecological and economic consequences, demonstrating that extreme drought impacts are not simply a matter of rainfall deficit but result from accelerated systemic feedbacks operating on compressed. Chapter 29. The Global Food System Ripple. The 2026 pre-trigger drought demonstrates that local environmental crises rapidly propagate through global food systems, illustrating the interdependence of agriculture, trade, and human vulnerability. The United States is a major producer and exporter of wheat, corn, and beef. Disruptions in these commodities immediately affect international supply and pricing. Early season crop failures in Kansas and Oklahoma, compounded by soil moisture deficits and thermal amplification, have already locked in a 31% reduction in projected winter wheat yield, while livestock liquidation reduces beef supply over a multi-year horizon. These domestic shortages propagate through international markets, affecting nations reliant on U.S. imports. Populations in sub-Saharan Africa, South Asia, and the Middle East, already sensitive to food price fluctuations, experience amplified insecurity. Simultaneously, teleconnection patterns reinforce global stress. The same Rossby waves contributing to pre-trigger drought across North America also reduce rainfall in India, compressing the monsoon season and impacting rice production. Indonesia's early dry season shortens planting windows. Southern Africa suffers prolonged drought conditions, necessitating emergency humanitarian interventions. These synchronous events highlight that the U.S. drought is not isolated but part of a planetary scale alignment where multiple agricultural regions experience simultaneous stress, limiting global buffers and alternative supply mechanisms. The pre-trigger conditions, therefore, not only amplify domestic risk, but also create cascading vulnerabilities worldwide, demonstrating that the timing of the drought relative to El Niño is critical. By the time tropical Pacific warming exerts its full influence, the system has already reached extreme stress levels. Financial markets, commodity flows, and global food security are already being shaped by early season losses, emphasizing that structural shocks can occur before observable climate events peak. Understanding these global ripple effects is essential. The pre-trigger drought in 26 provides an early warning, revealing how local extremes propagate internationally, challenging assumptions about market resilience and food system stability, and illustrating the compound risks inherent in a highly interconnected world. Chapter 30. Energy and Electric Grid Vulnerability. The pre-trigger drought of 2026 is not just an agricultural and ecological crisis. It directly threatens energy production and electrical grid stability. Hydroelectric generation, reliant on reservoir levels and water flow, is particularly vulnerable. Lake Powell, which supports turbines at Glen Canyon Dam, sits at roughly 23% capacity, approaching the minimum power pool threshold of 490 feet above sea level. Below this level, turbines cannot operate efficiently, reducing electricity generation for roughly 5 million households across Arizona, Utah, Colorado, and Nevada. Lake Mead downstream exhibits similar stress at approximately 30% capacity, triggering mandatory water delivery cutbacks that also impact hydroelectric output. Reduced hydropower increases reliance on alternative energy sources, typically fossil fuels, which are more expensive, less flexible, and environmentally detrimental. Energy demand is simultaneously increasing due to higher than average temperatures, placing additional strain on regional grids already operating near maximum load. The confluence of pre-triggered drought, heat amplification, and infrastructure limitations produces a precarious situation. And it misses us. The electricity shortages could coincide with peak summer cooling demand, creating cascading failures that affect residential, commercial, and industrial consumers. Moreover, water allocation for energy production competes with agricultural irrigation and municipal supply, introducing critical trade-offs that must be managed under extreme uncertainty. The drought's pre-trigger timing compounds risk. Decisions regarding energy distribution, reservoir release, and emergency resource allocation are being made before the primary El Niño forcing arrives, leaving little room for adjustment once tropical conditions exacerbate stress. The interconnectedness of water and energy systems illustrates that the 2026 drought is a multi-nation crisis, where environmental stress propagates through human infrastructure, creating economic, operational, and societal vulnerabilities. Understanding these energy impacts emphasizes the systemic nature of pre-trigger drought. It is not confined to meteorology or agriculture but influences core aspects of modern life, including power generation, grid stability, and economic continuity, all already compromised prior to the anticipated climate forcing. Chapter 31 Fire Agriculture Feedbacks. The 2026 pre-trigger drought has revealed how intertwined fire dynamics and agricultural stress have become, producing self-reinforcing feedback loops that amplify systemic impacts. Across the western and southern United States, early season wildfires, fueled by record low soil moisture and heat-amplified desiccation of vegetation, have already burned millions of acres. This not only destroys standing crops and pastoral lands, but also damages the soil structure, creating hydrophobic layers that reduce water infiltration. As a result, subsequent rainfall is less effective at replenishing groundwater or restoring soil moisture, further stressing crops and natural vegetation. Agricultural losses from pre-trigger drought and early fires are compounded. Reduced crop yields limit available feed for livestock, prompting accelerated herd liquidation, while charred landscapes increase the risk of erosion and nutrient loss, which impairs future productivity. Fire-induced carbon release contributes to localized warming, intensifying thermal amplification and increasing evaporative demand across surrounding fields. In this way, wildfire activity directly interacts with soil moisture, crop viability, and atmospheric conditions, creating a compound feedback system where each factor amplifies the others. The Southeast, particularly Florida and the Gulf Coast, exemplifies this dynamic. Dense subtropical vegetation, normally resilient to fire due to high moisture content, has been dried by prolonged drought and high temperatures, transforming landscapes into high-risk fuel beds. Even small ignitions can rapidly escalate due to heat, wind, and dryness, spreading to agricultural areas and disrupting harvest schedules. The pre-trigger nature of these events is crucial. The system is already primed for cascading failures, meaning that the impact of El Niño or additional precipitation deficits will layer on top of an already stressed environment, leaving farmers, fire managers, and water authorities limited options to mitigate risk. Understanding these fire agriculture feedbacks highlights the interdependence of ecological, climatic, and human systems, showing that early season wildfire is not just a symptom of drought, but an active driver of compounded agricultural and economic stress. The 2026 scenario underscores that effective management requires integrating wildfire dynamics, soil moisture monitoring, and agricultural planning, because each reinforces the pre-triggered drought and shapes the trajectory of cascading consequences. Chapter 32 Thermal and Soil Feedback Interactions. One of the most critical drivers of the 2026 pre-trigger drought is the interaction between thermal amplification and soil feedbacks, which produces conditions far more severe than precipitation deficits alone would suggest. Across the western and southern United States, Record high temperatures have increased the atmosphere's capacity to extract moisture, accelerating soil desiccation and plant stress. Dry soils fail to transfer solar energy into evapotranspiration, directing more energy into heating the ground in the lower atmosphere. This creates a self-reinforcing loop. Hotter surfaces increase evaporation, which further depletes soil moisture, reducing available water for crop, vegetation, and groundwater recharge. Plants under extreme stress close diameter to conserve water, limiting transpiration and reducing atmospheric moisture, which suppresses cloud formation and further diminishes rainfall. Across landscapes, these processes scale from individual fields to entire watersheds, creating a measurable reduction in regional moisture recycling. In 2026, these thermal soil feedbacks operate in concert with other pre-trigger factors, depleted snowpack, heat amplification, and pattern-locked high-pressure ridges over the U.S. The result is a drought that is self-reinforcing and accelerated, with ecosystem stress, agricultural yield reduction, and wildfire potential already locked in before the expected El Niño forcing occurs. The pre-trigger feedback loop also illustrates why standard hydrological or agricultural models may underestimate risk. They often fail to fully account for nonlinear interactions between temperature, soil moisture, and vegetation, which accelerate drought intensity exponentially. In practical terms, this means that water resource managers, farmers, and policymakers are making decisions in a system already operating beyond historical bounds, with soil and thermal conditions preloading vulnerabilities across multiple sectors. Recognizing the interactions between thermal and soil feedbacks is essential to understanding the 26 drought. It is not merely a question of rainfall, snowpack, or temperature alone, but how these elements interact synergistically to amplify stress across landscapes, ecosystems, and human infrastructure. Ensuring that pre-trigger conditions have already defined the trajectory of environmental, agricultural, and economic outcomes. Chapter 33. Agricultural feedback loops and market impacts. The 2026 pre-trigger drought has revealed the deeply interconnected nature of agricultural systems and global markets, where local soil and water stress rapidly translates into far-reaching economic consequences. Wheat fields across Kansas, Oklahoma, and Texas are experiencing terminal soil moisture deficits, effectively locking in a 31% reduction in yield for winter wheat compared to the 5-year average. Early crop failure triggers irrigation demands on the Ogale-Ola aquifer, which is already depleted by decades of overuse, further reducing soil and groundwater reserves and compounding stress for future planting seasons. Livestock are simultaneously affected. Cattle herds are forced into liquidation cycles, reducing domestic supply and creating price spikes that reverberate across international markets. The United States, a major exporter of both wheat and beef, thus becomes a conduit for global economic stress, affecting populations in sub-Saharan Africa, South Asia, and the Middle East, where food price sensitivity is high. These agricultural feedback loops illustrate that drought is not just a local environmental issue but a structural economic force, where soil deficits, crop failures, and livestock adjustments reinforce one another, amplifying both environmental and financial risks. Moreover, local losses propagate through supply chain dependencies. Feed shortages increase livestock stress, limited crop output reduces processing activity, and rising commodity prices influence import and export decisions worldwide. In 2026, these feedback loops are operating during the pre-trigger phase, meaning that even before El Niño fully develops, systemic vulnerabilities are already embedded across agriculture, markets, and food security. The interaction between soil moisture depletion, irrigation stress, crop failure, and livestock liquidation demonstrates the pre-trigger drought conditions have locked in both ecological and economic consequences, creating cascading risks that will persist for years. Understanding these interdependent agricultural feedbacks highlights the compounding nature of pre-trigger stress, showing how a single environmental anomaly can propagate through ecosystems and economies simultaneously. amplifying the impact of subsequent climate-forcing events and underscoring the unprecedented scale of the 2026 drought. Chapter 34: Water and Energy Interactions Under Drought. The 2026 pre-trigger drought demonstrates the interdependence of water infrastructure and energy systems, where drought-induced water scarcity directly threatens electricity generation, urban supply, and agricultural productivity. Lake Powell, held back by Glen Canyon Dam, is at 23% capacity, dangerously close to the minimum power pool of 490 feet, beyond which turbines cannot operate efficiently. This directly impacts hydroelectric generation for approximately 5 million households in the Southwest. Lake Mead downstream, at roughly 30% capacity, triggers mandatory cutbacks under the Colorado River Compact, affecting water distribution for urban and agricultural use in Arizona, Nevada, and Mexico. Reduced hydropower output forces energy managers to rely on alternative generation, often fossil fuel-based, which is more expensive, less flexible, and contributes additional greenhouse gas emissions. Elevated temperatures in 2026 exacerbate demand, with peak electricity use coinciding with record-high heat, stressing grid stability. Water allocation decisions are further complicated by competing demands: irrigation for crops, municipal consumption, industrial use, and fire suppression. Reservoir depletion also reduces the resilience of emergency response systems, as firefighting requires significant water resources. Snowpack deficits and accelerated early melt compound these problems, providing less inflow to capture in reservoirs, leaving systems structurally stressed before El Niño forcing arrives. This convergence of drought, energy, and water stress illustrates the compound vulnerabilities inherent in interdependent systems, where infrastructure failure in one domain propagates rapidly across sectors. The pre-trigger timing ensures that cascading effects, energy shortages, agricultural stress, and wildfire risk are already active, creating conditions that limit adaptive capacity when the full climate forcing manifests. Understanding the water-energy nexus in 2026 is critical. It demonstrates that the drought is not a simple meteorological event, but a systemic stressor affecting critical infrastructure, resource allocation, and societal stability across multiple sectors simultaneously. Chapter 35: The Role of Heat in Agricultural Loss. Heat in 2026 acts as a force multiplier for the pre-trigger drought, accelerating crop stress, soil moisture depletion, and vegetation die-off in ways that surpass historical droughts. Across the southern plains and Midwest, temperatures were consistently above historical averages, exacerbating the effects of already low precipitation and depleted snowpack. The Clausius-CLA-Perron relationship explains the mechanism. For every 1°C increase in air temperature, the atmosphere can hold approximately 7% more water vapor, intensifying evaporative demand. As a result, even moderate rainfall deficits translate into severe soil moisture stress, rapidly reducing plant available water and creating conditions for early crop failure. Wheat, corn, and soybean crops are particularly vulnerable during early vegetative growth, when soil moisture deficits lock in yield potential long before the growing season reaches maturity. Farmers are forced into difficult decisions regarding irrigation from depleted sources such as the Ogale Aquifer, balancing short-term crop survival against long-term water sustainability. In parallel, heat amplifies wildfire risk by desiccating vegetation and creating highly flammable conditions across both western and southeastern U.S. Ecosystems. The combination of thermal amplification, soil feedback, and vegetation stress generates a compounding effect. Drought stress accelerates plant mortality. Reduced transpiration increases local heating, and the hotter, drier environment further intensifies soil moisture depletion. This pre-trigger feedback ensures that the severity of the 2026 drought is already beyond what precipitation alone would suggest, setting the stage for catastrophic ecological, agricultural, and economic impacts. By examining the role of heat, we understand that early season thermal anomalies are not simply additive, they reshape the baseline conditions, making subsequent El Niño forcing more likely to produce extreme outcomes. The heat multiplier demonstrates that the pre-triggered drought has already locked in systemic vulnerability, emphasizing the importance of integrating temperature effects into drought forecasting, agricultural planning, and water resource management. Without accounting for these thermal-driven dynamics, assessments of potential yield loss, reservoir stress, and wildfire hazard would significantly underestimate the risks embedded in the 26 pre-triggered drought. Chapter 36. Soil moisture as a driving for soil moisture in 2026 is not just a passive indicator of drought. It is an active driver that shapes atmospheric, ecological, and agricultural outcomes. When soil moisture drops below critical thresholds, energy that would normally support evapotranspiration instead converts to sensible heat, warming the surface and the lower atmosphere. This accelerates evaporative demand, reduces relative humidity, and suppresses cloud formation, creating a self-reinforcing feedback loop. Plants under extreme stress respond by closing stomata, reducing transpiration, and further decreasing atmospheric moisture, which limits rainfall potential and perpetuates drying conditions. These processes scale from individual fields to watersheds, with widespread soil desiccation capable of suppressing moisture recycling over thousands of square kilometers. In 2026, prolonged pre-trigger drought has produced unprecedented soil moisture deficits across the southwest, southern plains, and parts of the southeast. Combined with heat amplification, depleted snowpack, and blocked atmospheric circulation, soils actively amplify drought intensity, locking in stress across crops, pastures, and natural vegetation. This soil-driven feedback explains why early-season crop failures, reservoir depletion, and wildfire risk were already severe before the anticipated El Niño forcing. The system operates non-linearly. Small differences in soil moisture can dramatically change outcomes for agriculture and ecosystem health, making it a critical determinant of drought severity. Soil feedbacks also interact with economic systems. Reduced soil moisture influences irrigation decisions, crop yields, livestock feed availability, and commodity prices, creating cascading effects across regional and global markets. Understanding soil as an active driver highlights that in 2026, drought is structurally embedded, with impacts preloaded across environmental, economic, and social systems. The pre-trigger drought is therefore not simply an anomalous dry period, but a self-reinforcing, multi-sectoral phenomenon, where soil moisture dynamics are central to the acceleration and severity of observed effects. Chapter 37. The Mega-Drought Amplification. The 2026 pre-trigger drought is the continuation of a multi-decadal mega-drought in the American Southwest, a prolonged period of aridity that has been steadily intensifying over the past 2 decades. Tree ring reconstructions extending 200 years demonstrate that the years 2021 were the driest sustained period in over a millennium, exceeding even the prolonged megadroughts of the 1500 seconds and 1600 seconds. Approximately 42% of the severity of this modern dry period is attributable to anthropogenic warming, illustrating that human-driven climate change has compounded natural variability, preloading the system for unprecedented stress. In spring 2026, this long-term baseline intersected with pre-trigger conditions, record low snowpack across 8 western states, heat amplification, and widespread soil moisture depletion created systemic vulnerability. Reservoirs, aquifers, and agricultural lands are already operating near critical thresholds, meaning that even moderate climatic forcing from El Niño would be layered atop an environment primed for extreme impact. Agricultural losses are compounded. Winter wheat, corn, and other staple crops face terminal stress before the main growing season, while livestock herds are forced into liquidation due to feed shortages. Water infrastructure, designed for variability but not extreme persistence, is stressed. Hydroelectric generation at Glen Canyon Dam and Lake Mead is constrained. Irrigation systems cannot compensate for depleted snowpack, and municipal supplies face rising pressure. Wildfire risk is simultaneously elevated. with desiccated vegetation and thermal amplification creating early-season fuel loads across western and southeastern forests. The mega-drought amplification demonstrates that pre-trigger conditions are not merely an early warning, they are determinants of seasonal outcomes, with cascading effects across ecological, agricultural, energy, and economic systems. This structural amplification means that even before the Super El Niño fully develops, impacts are already locked in, highlighting the unprecedented nature of the 2026 drought. Recognizing the interaction between long-term aridity, heat, soil moisture, and infrastructure underscores that the pre-trigger phase is not a temporary anomaly, but part of a broader systemic shift with consequences that will persist for years, shaping both domestic and global resilience. Chapter 38, Agricultural Collapse and Market Ripple Effects. The pre-trigger drought of 2026 has triggered early agricultural collapse, producing immediate and cascading market impacts across the United States and globally. Winter wheat, concentrated in the southern plains, is failing due to extreme soil moisture deficits and heat amplification, with early projections indicating a 31% reduction in yields compared to 5-year averages. This early failure forces farmers into high-stakes decisions regarding irrigation, often relying on the Ogeo or aquifer, whose long-term depletion risks further structural stress for future growing seasons. Livestock are simultaneously affected. Cattle herds experience forced liquidation, reducing domestic supply and triggering multi-year economic consequences, as herd recovery typically requires 3-5 years. The United States' role as a major food exporter amplifies these effects internationally, particularly for import-dependent regions in sub-Saharan Africa and South Asia, and the Middle East, where food security is acutely sensitive to supply disruption. Commodity markets respond, wheat and beef prices increase, affecting purchasing power, supply chain logistics, and trade flows. Pre-trigger agricultural collapse also interacts with environmental feedbacks. Reduced crop cover and vegetation increase soil exposure, accelerate evaporation, and elevate wildfire risk, creating self-reinforcing ecological and economic feedback loops. Water resources are further stressed as irrigation demands rise to compensate for lost productivity, exacerbating aquifer depletion and reservoir drawdowns. Importantly, these effects are already locked in before the full influence of El Niño, illustrating that pre-trigger conditions are sufficient to generate systemic consequences across agriculture, markets, and global food systems. Understanding these feedbacks highlights that the 2026 drought is not only an environmental crisis, but also a structural economic event, where early-stage crop and livestock stress propagates through interconnected systems, creating cascading risks that will persist for years, long before subsequent climate forcing compounds the problem. Chapter 39, Fire, Vegetation, and Soil Feedbacks. By 2026, pre-trigger drought conditions have created an environment in which fire, vegetation stress, and soil feedbacks interact to accelerate ecosystem collapse. Across the western and southeastern United States, early-season wildfires have already burned millions of acres, consuming both dry grasslands and forests that typically retain moisture. These fires do more than destroy vegetation. They alter soil structure, creating hydrophobic layers that impede infiltration, reducing the capacity of rainfall to replenish aquifers and soil moisture. Charred landscapes increase solar absorption, elevate surface temperatures, and promote further evaporative loss, reinforcing local heat amplification. Vegetation under extreme drought stress contributes to feedback loops. Plants close stomata to conserve water, limiting transpiration and reducing local humidity, suppressing cloud formation, and perpetuating dryness. These interactions scale beyond individual fields. Watersheds experience collective soil desiccation, and regional atmospheres reflect measurable reductions in moisture recycling. In agricultural regions, early-season crop losses are compounded by these feedbacks, as irrigation cannot fully mitigate pre-triggered deficits and wildfire damage can destroy seedbeds, pastoral deaths, and stored feed feeds. Livestock operations are affected indirectly. Reduced grazing quality, and increased feed cost for accelerated herd liquidation, further amplifying economic stress. Across ecosystems, fire-induced carbon release elevates localized heat, while dead biomass increases future wildfire risk, creating a self-reinforcing cycle that operates simultaneously across agriculture, energy, and ecological systems. The pre-triggered drought ensures that these processes are already active. The system has entered a state of structural stress, well before El Niño or other tropical forcing contributes additional precipitation anomalies. This multi-layered interaction highlights the complexity of compound drought impacts, where environmental, agricultural, and economic vulnerabilities are intertwined. By analyzing fire, vegetation, and soil feedbacks together, it becomes evident that the 2026 pre-triggered drought is not a series of isolated events, but a highly interconnected system of reinforcing mechanisms that determines the trajectory of continental-scale impacts long before the primary climate driver arrives. Chapter 40, The Systemic Pre-Trigger Legacy, as Spring 2026 unfolds. The pre-triggered drought has already established a legacy of systemic stress across the United States, redefining what extreme drought looks like in a modern, interconnected world. Across agriculture, soil moisture deficits have locked in early crop failure and livestock reduction, creating cascading economic effects that propagate into domestic and global markets. Water infrastructure is operating near critical thresholds. Reservoirs like Lake Powell and Lake Mead approach minimum power pools, limiting hydroelectric output, while aquifers are drawn down at unsustainable rates. Fire season has accelerated, with early burns amplifying vegetation stress, altering soil properties, and increasing subsequent drought vulnerability. Thermal amplification, driven by above-average temperatures, accelerates evaporation from soils and surface water, intensifying soil vegetation atmosphere feedbacks and locking in extreme stress, even before El Niño forcing arrives. Collectively, these factors demonstrate that the 2026 pre-triggered drought is not merely a function of precipitation deficits, it is a multi-dimensional, self-reinforcing system of environmental, agricultural, economic, and infrastructural stress. Globally, synchronized teleconnections link you. There's drought conditions to reduced monsoon rainfall in India, early dry seasons in Indonesia, and humanitarian drought in southern Africa, illustrating the planetary scope of interconnected vulnerability. The systemic pre-trigger legacy underscores a crucial insight. Much of the drought's impact is already determined before the anticipated Super El Niño reaches its peak. Decisions about water allocation, crop planting, energy distribution, and emergency preparedness are being made against a backdrop of extreme stress, where feedback loops across sectors ensure that even moderate additional forcing can have disproportionately severe consequences. The 2026 pre-triggered drought demonstrates that extreme climate events are increasingly structural, interconnected, and self-reinforcing, requiring an integrated understanding of ecological, economic, and infrastructural dynamics. By the time the full climate forcing arrives, the baseline has already shifted, and the legacy of pre-trigger conditions will define not just the immediate outcomes of this drought, but the resilience, adaptive capacity, and risk trajectories of the United States and its global partners for years to come. Outro reflections before sleep. As we close this journey through the 2026 pre-trigger drought, take a moment to let the scale and complexity of what we've explored sink in. From parched plains to depleted reservoirs, from record-low snowpack to early wildfire surges, the United States is experiencing a drought that has already rewritten the baseline of environmental, agricultural, and economic stress, before the climate forcing we expected even fully arrives. What we've seen is more than an anomaly, it is a systemic, interconnected event where soil, heat, vegetation, water infrastructure, energy grids, and global markets are all intertwined in feedback loops that amplify vulnerability. By understanding the pre-trigger dynamics, we gain a rare window into how extreme conditions unfold, how consequences are locked in, and how compound risks propagate both locally and globally. As you drift towards sleep, allow your mind to trace these connections, the silent rivers, the wheat fields under stress, the cattle herds dwindling, the skies too dry to form clouds, and the fires moving faster than humans can respond. These are not abstract statistics, they are signals, warnings, and lessons about the delicate balance of our environment and the resilience required to navigate a changing climate. Recognizing the complexity and scale of these systems empowers us to observe, plan, and respond more effectively, even as the world continues to surprise us with forces beyond any single season's rainfall or temperature anomaly. If this exploration has helped you understand the hidden mechanics of the drought, consider liking and subscribing so that more stories like this, stories that unravel the universe of Earth's interconnected systems before sleep, can reach those who need insight, awareness, or simply a moment to reflect on the vast, delicate network that sustains life. Let the lessons of this pre-trigger drought settle into your thoughts tonight, a reminder that the world operates in layers of subtle complexity, where timing, feedback, and interconnection define outcomes far beyond what any one moment alone can reveal. Sleep now with the awareness that what happens before the main event often determines the shape of the story, and tomorrow, as always, the Earth continues to write its own narrative.